Hello everyone, welcome to Machine Learning Pre-Conference Seminar at SAS Global 2020. My name is Kevin Lee, and I'll be teaching today's machine learning courses for SAS programmers. We're going to start with introduction of machine learning, and then we're going to discuss about its main concept, such as hypothesis function, cost functions, gradient descent, and running rate. And then we will talk about the process and workflow of the machine learning. And then we will also discuss the type of machine learning, such as supervised machine learning and also unsupervised machine learning. And then we're going to discuss the algorithms, shuffle vector machine, k-nearest neighbor, decision tree, random forest, XGBoost, largest regressions, linear regressions, k-means, clusterings. And then we also explain about how to validate or verify the trained model. And then we will talk about how to make machine learning better with hyperparameter tunings. And then we will discuss about the artificial neural networks, which is game changers of the machine learning, and its main concepts such as activation functions, loss functions, and also optimizers. And then we will talk about the deep neural network, which is actually make machine learning much more powerful and efficient. And then we're going to talk about how to improve the performance of deep neural networks with bias and variance and also regularizations. And then we also talk about the practical deep neural network implementation, such as convolutional neural networks and recurrent neural networks and transfer learnings. And then finally, we're going to talk about how machine learning AI is impacting our lives and how it's going to be impacting our futures at home and also at our careers. So let me introduce machine learning. About 2 years ago, my wife asked me, "Honey, do you know about machine learning? Do you remember the case or situation that somebody asked you, but kind of expect you to know?" And that's the reason that my wife asked. She knows that I'm doing programming, statistics, and most importantly, working with the data all the times. If you kind of looking at these three things, it is kind of like our job descriptions. We use SAS to all those programmings, and then we use statistic to predict and build the models. And then most importantly, we work with the data all the times. I'm sure that some of you already got asked that whether you know about the machine learning or not. So let's talk about what is a machine learning. The meaning of machine learning is applications of artificial intelligence that provide the system or machine to automatically learn and improve from experiences without being explicitly programmed. The key here is that improve from experiences without being explicitly programmed. So what is the difference between explicit programs and machine learning? Explicit programs pretty much provide rule-based programming. For example, when you like to categorize age groups, we define what age groups is going to be applied to what age. As you see this example, if age is less than 65, we put that age or patient into age group 1. If it's between 65 to 69, we put that into age group 2, and so on. In the machine learning, we don't apply rule. We're just using data and then algorithms to decide what age going into certain age groups. So there's no rule-based programming in machine learning. So how does machine learn? Let me ask you questions. can you tell me about these pictures? Yes, it is a cat. Then how do we know that it is a cat? We actually seen this before. Human learned from our experiences. We learned by singing it, taste it, hear it, feel it, and so on. What about machine? Can machine see this one? Can machine feel this? Or can machine taste it? Or hear it? Machine actually learned from the data and then algorithms. Just like we see cat's pictures for thousands of times and we figure out what is a cat. So when we actually trained machine with the cat images and then algorithms, eventually when machine see the real data, they could tell whether it's a cat or not. So key here thing is that machine will learn from data and algorithms. It is their experiences, just like human learn from our experiences. In the algorithms, there are actually three key functions. Hypothesis functions, such as y equal x plus b, and also minimize functions, cost function to minimize, and also gradient descent, which is optimizers. So we actually put the input data with the output data such as x0, x1, x2, xn, and y, which is answer, and we actually train our algorithms with this data, and the machine gonna learn from their experiences. So what is the main concept? We're gonna talk about three concepts, which is vital about the machine learning. If you understand about how these three concepts or functions work together, then you actually understand how machine learned. We're going to introduce hypothesis functions, cost functions, and gradient descent. Hypothesis function is machine learning algorithms and model that we will train with the data. There are a couple types, which we're going to discuss later in our courses. Linear regressions, largest regression, support vector machine, decision tree, and artificial neural networks. And then it is main function and formula is theta 0 x0, theta 1 times x1, theta 2 times x2, and so on. This is one of the examples of hypothesis functions. And then we try to find about the parameters of these hypothesis function. That is the ultimate goal of the machine learning algorithms and trainings. Cost function, another one is a loss function, is the measurement of how well our hypothesis function fit into the data. So basically, it is a difference between actual data point and hypothesis or predicted data point. For example, is for linear model, square mean error is the cost functions. Gradient descent is, in other words, optimizers, which is engine that minimize cost functions. By doing this, we are able to find the proper parameters or optimize parameters. So let's kind of talk about how the machine learning get trained and also workflow. This is probably going to give you about the high level about how machine learning is going to work. Let's kind of imagine that we are teaching young children about the cat pictures, which they never seen before. First step we're going to do is show the first set of the pictures, which may contain cat and dog and other pictures. And then tell the kid that some are the cat pictures and some not cat pictures, maybe dogs. And then you could explain why there are pictures, these are cat pictures, and why they're not cat pictures. And then we again show the next set of the pictures. We're actually doing this process, showing the pictures and also explain why some are pictures, some are cat pictures, some are not cat pictures. We repeat this about a couple times until children understand which are cat pictures in general. So some kid probably gonna figure that out about maybe 100 pictures, and some kid probably about 120, 150. It depends on kids. But eventually, if we showing the pictures, thousands of pictures, then kid will eventually figure that out. Machine learning is not so much different about teaching kids about the cat pictures. Our first step is about the machine learning training process is we select the data and hypothesis functions, and then start with the random parameters of the hypothesis functions, such as data, and then process first set of data in hypothesis function, such as we showing first set of cat pictures, and then we find the predictive value from hypothesis functions, which means that kid will tell us which are cat and which are not cat. In machine learning process, we're gonna calculate the cost function, pretty much about the difference between actual and predictive values. And then we minimize cost function using gradient descent. What that means is that we actually tell the kid which are cat, which are not cat. The next function of machine learning is update the parameters of hypothesis function based on cost function minimization. You could see more detailed information when we show by step with some example. And we repeat step 3 to 7 with a new set of data until cost function becomes 0 or at the lowest point. Let's look at the example. First step of machine learning is that select the data and hypothesis function. Let's imagine that we have this data point with the x and y. You could see that this x point, we got y point. Another x point, we got another y point. And then we select the hypothesis function as a linear regression, y data times x. The next step is we start with the random parameters of hypothesis function. Remember we have a data x. So now let's imagine that's kind of set that we're gonna set the data equal 4. And then let's process first set of data in hypothesis functions with the initial parameters and predict the value from hypothesis function. We actually set our initial parameter as a 4. So if you plug this number, this first set of x data, 1, 2, 3, and then our y hypothesis function become 4, 8, 12. And then next step for machine learning does is it calculate cost function, which means pretty much the difference between actual and predictive value. The linear model cost function is a square mean errors. We're going to talk more detail later on, but that is a cost function that we're going to use for linear model. So the difference between the cost function of actual value and predictive value is become 9.33 if you plug all these numbers together. 2 minus 4, 8 minus 4, and 12 minus 6. If you actually plug this number, it goes something like this, right there. So cost function versus parameters. If you plug this cost function versus in different parameter, that is a shape we're gonna see. When the hyperparameter and then parameters equal 4, then the cost function is gonna be 9.33. when it's going to be 3, it's a 2.33. And then when hyperparameter is going to be 2, then it's going to be 0. So our goal is to find to this 2 using the data and then algorithms. So here comes the gradient descent. The definition of gradient descent is an engine that minimizes cost functions. So it is actually the process of getting to the lowest error value, which is the cost functions in the machine learning algorithms. It is kind of walking down in the mountain to find the goal located in the valley. So gradient descent actually helped the cost function become less and less up to the optimal cost function point. So what machine learning does is it tries to minimize cost function using gradient descent. It is more about calculus right now, but it takes the derivative of the cost function since it will give the direction to the moving forward. And then it moves step down so that it's going to be minimize cost functions. And then running rate is another concept about the cost function, and it will actually show how much it will change based on the gradient descent and also cost function. So as you see the point that if the parameter is on this side, on the right side of the optimal point, it's gonna be the negative, and then if it's on the left side, and it's gonna be positive. So that where your parameter is gonna be right, it's gonna go into the lowest point of the cost functions. So it will help that cost function get lower and lower based on the parameters. And running rate is determined how fast it will learn. That's why you call running rate. For example, let's say the parameter is 4, but the running rate is 0.1, then it will decrease to 3.8. However, if it's a 0.5 as a running rate, then it's gonna decrease kind of 1 point. So it's gonna go down to 3. So it will determine how fast the machine will learn based on the parameters perspectives. So the next step is the machine learning will update the parameter of the hypothesis functions based on the cost function using gradient descent. So initial hypothesis function is starting as a 4x because data is set to 4 initially. And then cost function become, because there's difference between actual point, which is 1, 2, 4, 6. So it calculates cost function and become 9.33. And then using gradient descent, the parameter, which is data, gonna be changed from 4 to 3.8. And then our modify hypothesis function using the first set of data become 3.8. And then next step is gonna be 3.6 and 3.4 and so on. So we repeat 3 to 7, train with a new set of data, calculate other cost functions. At the second iterations, the cost will become 7.56, and the gradient descent is going to be 3.8 to 3.6. And then for after second iteration of the data, the trained data, that we get another hypothesis function is a 3.6x. So these iterations from step 3 to 7 will go on until the cost function get to 0, like theta 0 theta equals 0, or if there is no longer decrease or no more data, basically. So basically, the cost function and gradient descent to find the best model by going through iterations. From starting this point, next point, next point, next point, next point, next points, and then our hypothesis function change each time, each iterations until it hit to the 2x, just like this data. So in the graph perspective, the model training machine learning, starting the hypothesis functions, going through a new set of iteration of data, and then calculate the cost functions, and apply gradient descent, and update the parameter of hypothesis functions. It go on until the cost functions get to 0 or the lowest point, or the specified set of iteration. You actually set this iteration about in a certain time, maybe 100 iterations, or if your cost function becomes 0 or at optimal point, so that we could actually get the best model that could provide the best predictive value. So in this best model, then if your x in somewhere this point, and you also provide the y values using the best models. Another interesting is that with the same model and same hypothesis functions, usually more data provide a better model and better predictions. However, if you get a different data and it provides different model, which is different slopes or data, and it provides different predictions. So one good thing about machine learning is that when your data change, your model also change automatically. Because sometimes trends, either market trends or some of the data you're gonna get is change, then you don't need to do program all over again. Using the current model, just train with the different data. Then it will work just like machine learning run by itself. However, if you get the bad data, it will provide bad model and it will get the bad predictions. So data is most important things in machine learning. One of the most important things in machine learning. We call that garbage in and garbage out. So there could be bad example. We're not sure whether it's a cat, ant, or humans. So now let's talk about machine learning types and also its algorithms. Let's say we do have a different problems: constructions, airlines, electrical engineering, hospital, or farms. Different job usually means different professions and different problems. So for each problem that we have, such as constructions, flying airplane, fixing the electronics, carrying the patients, raise farms, we need to have a different professional, which means find the right person for that some specific jobs and problems. Machine learning is kind of very similar way. We have to find the right algorithms for some specific problems. So our algorithms based on what kind of problem that we're gonna have and also what kind of data we're gonna have. And then you find the right algorithms. And then we actually train that algorithms. There are two types of the machine learning data. One is supervised machine learning. What I mean by is that it has a input data has a label, which means it has a correct answer. Like in this case, it has a Y result. It usually for some specific purpose. And then there are mainly two types: the classifications for the testing output values and regressions for the continuous output value. Another type is unsupervised machine learning, which means input data are not labeled, which means there's no correct answers. It is popular for exploratory analysis, and then its main type is that clustering analysis, which k-mean clusterings. In supervised machine learning, there's a classification. classification pretty much about the categorical target, either binary or multiple classifications. Example is that is output is usually yes or no, or 0 to 9, or sometimes mild, moderate, and severe. And its main algorithm is largest regression, support vector machine, K nearest neighbors, naive Bayes, distant tree, random forest. XGBoost is kind of popular algorithms in machine learning classifications type. So let's talk about the classification algorithms. Support vector machine is one of the most popular classification model, both binary and multiplication classifications. And it is especially for the complex but small and mid-sized dataset. It works best for the binary classification, which means yes or no, or class 1 and class 2, as you see in this graph. And it is actually easy to train. And then what it tried to find is that in machine learning is it tried to find line or hyperplane that divide 2 or 3 classifications, 2 classes. Its hyperparameter is a kernel, either linears or polynomials, and also gamma and the margin, which is how far is different. And usually it tries to find about the function that determine the separation between 2 or 3 classes. As you see this graph, in the 2 dimensions, it's going to be a linear line or sometimes polynomials. If it's 3 dimension, which is 3 data points, then it could be 3-dimensional plane. So once the model is trained, if data point is fine on this, let's say once the support vector machine find and then trains, so it actually find about these hyperplane functions. If data point is gonna be fine on this area, which is left side of this hyperplane, then it belongs to this class. It's a right side, then it belongs to this class, maybe class 2 and class 1. So benefit about this support vector machine is that it really works well with a clear margin of separations and then also very high dimensional spaces. High dimensional space means that there is a lot of data points, x1 to maybe x100 or things like that. And this kind of unique about support vector machine is that it works well even though number of dimension is greater than number of the sample, which is not a case in most other machine learning algorithms. Its weakness is that it actually requires a lot of computational power. So it doesn't work well with large data. So big data application, this SVM is not ideal machine learning algorithms. And then it doesn't perform well when data has a lot of noises, which means unclean data. It doesn't work well with the unclean data. Actually, SAS also has machine learning the package such as SAS Visual, data mining, and machine learning. It provides the data mining pre-processing and supervised and unsupervised machine learnings and also post-processing. It's kind of easy to use and click machine learning algorithms interface. Such as it has a data mining process, either anomaly detections or clustering, feature extractions and filtering, imputations. So it kind of provide that, rather than programming, it could kind of provide how to prepare some of the input data so that it could apply to the machine learnings. And then machine learning has a Bayesian networks and distant tree, the forest, gradient boosting, linear regressions, largest regressions, artificial neural network, and support vector machine. So it has a couple of that machine algorithm that we can actually apply into our model. So it has a support vector machine, and then once you click this, once you actually prepare your data, and then you could click this subproductive machine, and then you will open little box, and then data coming in, and you could set up some of the hyperparameter, such as we talk about the chronos. You could make a linears or polynomials, and so on. And then once you got it, and there's this run button, then it will run this model, and it provide the result about this model. K nearest neighbor is one of the actually very useful machine algorithms. It is very simple and easy to implement. Then it could also apply to the classification and regression problems, which means that it could apply to a distinct output and also continuous output. We actually call this the lazy algorithms. I thought it's kind of funny they call this lazy, but what happened is that we don't really train KNN machine learning because KNN remember the trained data point, and then it will calculate and you memorize that data point, and it will apply the data point with the test data. Let me give you an example. In this example, let's say we do have about we have a training data, and we actually run this training data into KNN algorithms, and then KNN remember each data point. So when new test data comes in, such as this area, that it find the nearest neighbors. We set up K as a 3, so we find about 3 nearest neighbors. So 1 from this side, 2 from this side. So as you see that for this data point, it has a 1 group 1, and it has a 2 group 2, group B. So based on the result that we got from the nearest neighbor, this test data is gonna be class B. However, the interesting is that we have a situation that when K equals 3, provide more class B, but larger case K, which is K7, provide more class A. So it is very important for KNN to determine what is the optimal test optimal K, so that it could provide the best predictions. The benefit of this KNN is it could train really fast, and it's very simple and easy to implement, as you see this, and then it is very useful for non-linear data. However, it has a weakness. It could be slower and costly for the time and memory in predictions. And then it might be ideal for the large data because you have to memorize all the training data point, and then you have to calculate in the predictions. Usually all other algorithms do calculations in the training data, so test data doesn't need a lot of calculation, but KNN require a lot of calculations in the prediction phase. So it doesn't work well if you need to have a quick and a fast prediction time requirement. Decision tree is one of the most popular machine learning algorithms because it provides very visual representations and easy to explain to other people. So it could be applied for both classifications and regression, even though it is much more popular in classifications. If you kind of little bit discuss about its architectures, and here's a root node, and then internal node, and then branches such as here warm and cold and yes or no, and also it's splitting based on its conditions, and then leaf node is such as decisions, which is non-memo, memo. That is a leaf node which is making decisions. Before we actually provide the one-year decision tree, we could set some of the hyperparameters, such as what is the maximum number of the features, which is variable we're going to use, and also the depth of the branches. How many branches? Here in this case 3, but you could go into 4, 5, and 6. And also criteria, the measure of the quality of the split, which is Gini or entropy. The algorithm that decision tree use is pretty much Gini and also entropy. Gini is a measurement of the impurity, and entropy is a measurement of disorders. So the whole point about is you try to minimize Gini impurity and also entropy. So it kind of use cases. So for example, let's say the problem that we like to solve is what is the conditions of the patient who survive, and then we actually input a feature is going to be sex, age, and whether it's treated or not, and also the label is whether patients die or not. So in this example, it's just a hypothetical example, but if the patient is a male, if the patient is not male, then everybody is alive. And if it's yes, and some is die, so look at the next feature, which is age, whether age equal greater than 65, and then the patients die. And if it's no, then patient's still alive, but whether it's treated or not, if it's treated and patients are alive, but it's not, then patients die. So as you see that it gives a clear conditional cases about each features, how each feature impact the output. So decision tree is very useful to find about how some of the result was impacted for the input variables. And then also the SAS visual data mining and machine learning interface or package and provide decision tree. You select the decision tree with the data, and then you could actually set some of the hyperparameters, and then you could run this in your programs. And then it will actually provide the result. As you see this, it will actually provide the result. How many branches it has, and what was the condition about each branches, and what's the output of a condition, and how it is going to impact the result or the ultimate output of the data coming in. Random forest is another popular machine learning algorithms. It is a so-called ensemble of decision tree, which is basically using the multiple decision tree. What happens is that, let's say you have about thousands of patients, and then we actually splitting the 1,000 patients into maybe about 300 patients, about 20 samples. So that those 20 times we have a 20 decision tree, and then it actually provides the result about the class A and class B and class C, and then we actually take the majority vote about the output. So random forest is more about the aggregations or average of the decision tree, and it actually provide more general or better generalizations of performance of, and it is less subject to overfittings. So random forest is a very popular machine learning algorithms that are used for a lot of implementations. SAS visual data mining and machine learning package also have these options. So you actually click the forest, random forest, into your interface, and then you provide the hyperparameters option that you could actually select the option, and you could run this, and you provide the result about random forest. Another popular machine algorithms from the decision tree is XGBoost. Rather than parallel machine learning of the random forest, it is go into boosting, more about sequential trainings. In the random forest, we notice that output, we actually take the average or the most vote of the output. However, in the XGBoost is you actually train from output again. You got another output that we actually train from the output again. So you actually usually provide the performance compared to random forest. So it is another advanced ensemble model of decision tree that provide a better performance in terms of machine learning perspectives. And then it is It actually extremely fast compared to parallel computations, and then very efficient. It is very versatile. You can use for extract the variable importance, and do not really require a lot of feature engineering. And it also has a regularization, prevent overfittings. However, it only works with the numeric features and not working with the outliers. And it is difficult to set up because it is dependency of the previous trainings. But you're probably gonna see a lot of XG boost machine learning implementations into recent and more advanced machine learning algorithms. And also SAS visual data mining and machine learning package also has this gradient boosting as one of the options. Now we talk about logistic regressions. Logistic regression probably the most popular machine learning the classification, which is binary output algorithms, because it could take continuous and categorical variable as an input variables, and then it works really well in a lot of situations. For example, when you try to predict if tumor is malignant or not based on tumor size, at a certain point of size, it become highly likely tumor rather than benign. But basically, logistic regression is combination of two functions, logistic plus regressions. Regressions such as theta x plus b, and then logistic is pretty much a sigmoid functions. If you look at about these architectures, we get input variable times its slope or parameters, like x1 times theta 1, x2 times theta 2, and x3 times theta 3, and so on, xn times theta 1, summation plus biases, which is, mathematics, we're just going to go theta 0 times x0. So we actually adding all this together. After that, we actually apply this into sigmoid. So basically apply that value to that e to the minus c. And then our output is going to be the from 0 to 1. Let's say, for example, if have a slope as 2156.5, and if you plug this number, and z, we got all the summation. After all this calculation, we got 13.5 as a z, and we're gonna plug that information into sigmoid, and then we got 0.99998. So it's close to 1. Also, the SAS visual data mining and machine learning platform also has logistic regressions as a part of the machine learning package. Regression is, I think we kind of all know about regression is. Regression is pretty much about the continuous output. So we actually predict the continuous output. It could be any number from minus infinity to infinity. Example is you could predict the house prices per square foot and so on. And it has linear regressions and like this graph, or polynomial regressions, and decision tree or random forest also provide regression, even though they are more fit into classifications. So in many cases, in the regressions problem, that we usually using about linear regressions or polynomial regression models. And its hypothesis function is very simple, like theta times x plus weight. So like y equal 10 plus 2x. It's a simple linear regression model. And its cost function usually used for the accuracy of regression model, such as square errors, mean square errors, and root mean square errors, and absolute error, and things like that. SAS visual data mining and also machine learning package also has this linear regression as options. We actually talk about supervised machine learning so far. And then now there is an unsupervised machine learning, which means that non-label input data, which means no correct answers. Usually it is done for exploratory analysis. And then, basically the clustering is the most popular one, which means assign the set of observation into subset, which is cluster, so that the data in the same cluster are more similar to each other than those from different clusters. So basically, we find these 3 clusters from this data point. Most popular one is a K-mean clusterings, and it is quite popular in industry nowadays because not all the data has answers or label. So this is the one that we're using for the lot of big data, which we do not have an answer for it, such as grouping of documentations, or grouping of the musics, or grouping of the movies, or finding customers that share similar interests based on common purchase behaviors. So basically about the documentation segmentations, or customer client segmentations, image segmentations, and then recommendation engines are the popular ones we're using for the K-mean clusterings. So K-mean clustering is one of the most popular in unsupervised machine learning. It's the simplest, then probably most popular unsupervised machine learning algorithms. As we discussed before, it grouping similar data points together and discover underlying patterns. So we kind of find about what is a K using those data. So basically, the K-mean clustering algorithms identify K number of centroids and then allocate every data point to nearest clusters while keeping centroids as small as possible. So this example, we try to find 2 clusterings, and then the clustering algorithms try to calculate every data point and then try to find the optimal K usings, and also try to find the K is the centroid of these K values. However, sometimes you have to kind of find about optimal point. And a lot of time the machine learning is the combination between the programming and also statistics or model. So if you require a lot of programming, it is recommended not to use too many computing powers. So we try to find optimal data point using that, cost functions and also the K-mean clusters. And SAS visual data mining and also machine learning package has this option as well too. So you could pick the clusterings, and then you set up some of the hyperparameters, and then run this one. Then you'll find about clustering analysis. So now, once you actually train your model, one of the most important thing is how to validate or verify the trained model, which means how accurate that is. I've been working as a stat programmers. So many times if we actually develop some of the report and also the data set, there also need to be second programming, which verify whether what I produce is correct or not. Kind of same thing. Once you train your model with the training data, you also need to verify the trained model with the test data. So in many cases, a lot of you probably know about the SDLC, System Development Lifecycle. And part of the validation process is actually we do, in SDLC, we actually do validate the output, such as based on user requirements or based on functional requirements. Machine learning also probably similar way. For example, let's say you do X-ray diagnosis. You build a model to that. The model look at the X-ray and it predict whether he has the patient has cancer or not. And then let's say you have your model performing about 90%. And then using another data point, you have to validate whether this model perform 90% or not. So in this machine learning algorithms, when you prepare data, we prepare data into training data and test data. The training data is one that we're gonna train our machine learning models. And then we actually using the test data to model evaluations. So we actually set some of the threshold for the model evaluation, such as accuracy is gonna be 80%. So one person, let's say, you could this way, one person actually train your model, another person using that test data to evaluate the model. So this test data never change. We keep as it is, and then this person cannot see this test data. Once you build a model, train the model, we pass on to the evaluators, and then they evaluate it, and they usually go over 80%. Otherwise, it's go keep training and trainings. And then if doesn't get evaluate doesn't pass, then another time that the trainers using different algorithms or using more data or to change some of the hyperparameters. So in many cases, we measure the accuracy or precision we call for the classification metrics. But sometimes for the regression, we're using the SME or SAE or ranking metrics and statistic metrics, correlations, and computer vision, and also NLP metrics that we're going to talk about a little bit later in our courses. And one of the most popular the classification metric is confusion metrics. We talk about you actually evaluate accuracy of the model and precision of the model, recall of the model, F1 score of the model. A lot of time that F1 score is one of the most popular classification metrics evaluation. And some cases we also using the ROC as using the sensitivity and specificity as a part of the metrics evaluations. We also could set up the model comparisons or evaluation using the F score here in the SAS Global Data Mining machine learning package as well too. And it actually showed some of the output that we have. Hyperparameter tuning is one of the important part when you actually try to make your model perform better. Hyperparameter is a setting of the algorithm that could be adjusted to optimize the performance. So a lot of time that hyperparameters are not really easy to determine out of time. So usually we tuning after the model is trained, and we actually continue to train the model using hyperparameter tunings as well too. Artificial neural networks, in other words, ANN. It is the most powerful machine learning algorithms, and then it is game changers. Interesting is it works very similar to human brain, human neural networks. And its main type is deep neural networks, convolutional neural network, recurrent neural networks. And its architecture has artificial neurons like this, input layers, hidden layers, and then output layers. So let's compare between human neural networks versus artificial neural networks. As you see the human neural networks, it has or it receives neurotransmitter from neural networks, and then you get multiple signal from other neural networks, and then it process and also it send it out to the next human neural networks. And then it has about 100 billion human neural networks. Artificial neural networks work very similar to human neural networks. It receives the data and input, and then it processes it, and it also go into another process, and then it send it out to next artificial neural networks. Something like this. It receive it, process it, it send it to the next artificial neurons. So if you look at about its architectures or formula about artificial neurons, it works something like this. It has an input variable from x1, x2, x3 to xn. It is a numeric value that go into artificial neuron model. And then it can multiply by weight, actually corresponding weight. y1 for x1, y2 for x2, y3 for x3, and so on up to yn to x1. And then it also have a bias. So if you do multiplications and then summations, so it works something like this. The G1 from here is summation of the multiplications of input variable and its parameters, such as x1 times y1 plus x2 times y2, x3 times y3, and go on, times x1 times y1 plus biases. Once we do summations of these input variables to the G1 output, and it also go into another function such as activation functions, and then we get output as A1. We're going to talk more detail about these activation functions, and it works exactly something like this. Let's look at the example. Let's say our weight is going to be something like this. We have a 4 input variable and then 4 weight and 1 bias. And if you actually plug all those information, such as input variables such as 255, 231 up to 122 times weight plus biases, we get 0.98371, and we plug this number into activation function, which is in case sigmoid, then we get 0.727844 as output. I think we've seen this one in previous algorithms. It is kind of very similar to logistic regressions. So let us ask question, what does artificial neuron learn in these cases? As we discussed before, the ultimate goal of machine learning training is to find or learn optimal parameters. In this case, W1, W2, W3, W4, and biases. So the reason that we do all those calculations and training is we try to find about Y1, the weight variables, and then bias variable, which is parameters. So the way artificial neural learned is exactly the same as we actually talked about before in machine learning trainings. It calculates the cost function, which is difference between actual output and predicted values. And then we using the cost functions and gradient descent to find about the parameters, such as weight and biases. So let's look at about the artificial neural network architectures. As you see this example, we have input layers, and we have 2 hidden layers, and we have 1 output layers. And input layers, we have 3 features, which means x1, x2, x3. First hidden layer, we have 4 artificial neuron, 1, 2, 3, 4. And second, we do have 2 neurons, 1, 2 in second hidden layers. And then output layer, we have 2 output. So in terms of weight wise, For hidden layers, we have a 12 weight. Let's calculate. For this hidden layer, artificial neuron hidden layer 1 is that we have a 3 input, which means there's 3 weight. And then second neuron in hidden layer 2 is we also have a 3. So if you times 3 times 4, then we have a 12 weight in hidden layer 1. What about hidden layer 2? We have a 2 neurons, and each neuron receive 1, 2, 3, 4, which means that we have a 4 weight. So 2 times 4 is gonna be 8. And then in our output layers, we got 2 neurons, and it received 2 input, so it's gonna be 2 weight, so it's gonna be 4. And then biases for hidden layer 1 is that 1, 2, 3, 4. So altogether, the parameter that we have to find about this example, about 32 parameters we have to find, or 32 parameter we will train. We briefly talked about activation functions in previous artificial neural network. So there are about a couple examples about activation functions. So activation function is pretty much of a node that added to the output of neural networks. Sometimes it could be added between 2 neural networks too. And its purpose is to provide the boundary of output. There are a couple activation functions. First one is a linear functions, which means that it provides exactly the same thing as comes in. And the sigmoid or logistic function is that it limit from 0 to 1. So if the data comes in, or the summations of those data comes in as 2, then it's going to be about 0.8. And if you go by 7, then it's pretty much go into 1. Same as the other way. Hyperbolic tangent function is gonna be range from -1 to 1. So it is mainly used for the classifications of 2 classes. Value is probably one of the most popular activation functions. It is pretty much gonna be everything below to 0 is gonna be 0, and then other thing is gonna be straightforward. So it is used between the neural networks, and it is very popular for CNN and DNN. And its main purpose is speed up the calculations. Softmax is another function that really popular that will turn number into probability that sum to 1. Let's say that we have a 4 output, such as very happy, unhappy, and happy, very happy. As you see that soft function provide a probability, saying that the data provide 10% very unhappy, 20% unhappy, and 55% happy, and 0.15 very happy. So activation, this softmax activation function will provide the output such as happy as a final output. And it is very popular activation function for multiple classifications, for neural network, recurrent neural networks, and then NLP, natural language processing. So let's look at how it's gonna be turns out into activation functions. We assume that all those inputs such as x1, x2, x3, x4, and weight and bias is the same. And then we put or use different activation functions. Let's say it's g equal 13.5. If linear function is activation functions, then we got 13.5. And sigmoids, we got 0.9999. And tangent, we got like almost 1. And the value, we got 13.5. However, if g is minus 0.4, our linear function is going to be 0.04, and then sigmoids we got 0.4, but tangent we got like minus 0.37, and value we got 0. So as you see this, however input that we're going to have, activating function determine the boundary of the output and also change the output as it fit the purpose of the machine learning algorithms. We actually talk about one of the most concept is such as hypothesis functions, cost function, and gradient descent. Let's talk more detail about it in next 3 or 4 sections. First, loss function. Loss function is pretty much same as cost function. It is a method that evaluates how well your algorithms fit your dataset. If your prediction of the model is off a lot, the loss function will provide higher numbers. If the predictions of model is good, the loss function perform or provide the lower numbers. There's a 2 type of a loss function. It is pretty much based on the output or label of your data. One is regressive loss functions, and another one is classification loss functions. Regressive loss function is the one that for continuous target variable. And then usually activation function is going to be regression that we talk about or provide in the first example. And they usually provide 2 types or 3 types actually, the mean square errors and mean absolute errors and smooth absolute errors. And it will determine by the data and of the uses of your output. The classification loss function is for the classification target variable. Usually there are 2 types. One is for the binary, and another is a multi-classifications. Binary is pretty much about whether it's going to be 1 or 0, or yes or no. And then popular one is a sigmoid. Also, another is a binary cross entropy loss function. These are one of the most popular one. For multi-classification is that it is basically for the multi-target, such as 0 to 9, happy, unhappy, very unhappy, things like that. And then multi-cross entropy loss function is one of the most popular one. So when you're looking about loss function, when you determine loss function for your algorithms, then usually for binary cross entry loss function for binary classifications, and multi cross entry loss function for multi-target. Optimizer in machine learning is kind of similar as gradient descent. Its goal to minimize cost or loss functions. It will calculate change the weight or parameter of the model so that error from the cost function will get lower and lower at each iterations of a new dataset. It's kind of like walking down in the mountain to find the goal located in the valley. And then its main parameter is running rate, like how much you're going to walk down for each step or how much machine will learn each iterations. So this kind of like overview of optimizers. Then you could actually looking about the batch gradient descent or stochastic gradient descent and adaptive learning rate and atoms. Usually atom is most popular because it is adaptive. It provides adaptive learning rate. What they mean by is that when the first set of iteration learning rate is going to be high, however, it's going to go near to the optimal cost function, then it will become less. So your learning rate kind of adjusting based on your cost functions. So this is another very good machine learning algorithm that we could probably use a lot in our machine learning implementations. It is called deep neural networks. Another one is that we call deep learnings. So deep neural network is pretty much about aggregate of individual artificial neurons. It is a kind of type of that artificial neural networks, and that we consider is a deep when hidden layers go more than two. So as you talk about artificial neural network, is a basic architecture is input layers, hidden layers, and output layers. And each layer is made up of a set of neurons, such as there are 4 neurons in first hidden layers, and then each nuance is fully connected all the neurons in the layer before and sometimes after. So example of deep neural network is detect whether patient will have a cancer or not. So input variable gonna be age, sex, race, weight, height, family history, and outcome is gonna be yes or no. And we can also detect number from 0 to 9 from images. Kind of input variable is going to be image data, such as 28 by 20 pixel images. Then output is going to be 0, 1, 2, 3, 4, 5, 6, 8, 9. And also for pharmaceutical industry, we could also detect a event from the text messages. So input variable is going to be the text, comment from social media, or report from the site or hospital, and that outcome is going to be whether those text or message is going to be adverse event related or not. And also you could detect sensitivity from text message, such as we could have an input variable as a blocks, comment from social media, then outcome is that you'll be very happy, unhappy, happy, very unhappy. The SAS also provide that neural network package in visual data mining and machine learning package. As you see that there's an option for neural networks. You actually click it and drag into the data after data preparations, and you could actually connect this one. You could set up the layer, such as you set up to 3 hidden layers, and then the number of a neuron for per layer is going to be set up to 10, and also activation function is a ton and things like that. So you could have an option to set up the hyperparameters and also the architecture of the deep neural network using SAS visual data mining and machine learning package. Yeah, that's another hyperparameter you could set up in all those areas. Yeah, I just see that SGD is a stochastic gradient descent, which is the optimizers, and the iteration, how many times you're gonna try. And so you could actually set up all those the option, which is hyperparameter, using that SAS, visual data mining, and machine learning. One of the good thing about this package is that it is very easy to use, and also very intuitive, and also some of the things that you could already set up as a default. And you could also see the what is hyperparameter you can use for this machine learning algorithms. So let's also talk about how we could improve deep neural networks based on the biases and also variance and regulations. Once you train your model, there's a situation you kind of notice is that could be underfitting, or it could be overfitting. Underfitting is more like about your model doesn't really represent you well. Remember, sometimes you actually wear the clothes that it's not really about you. It doesn't really tell about yourself, kind of like that. And overfitting is that looks really good at the moment, but not really all the time. It only fit into certain situation. For the machine learning is that only for certain data point. For example, after you model your data and you train your model, underfitting is that as you see that your data point is represents something like this, but you actually get the model in a straight line, and it is probably as a really not good performance in terms of accuracy, and also it doesn't really represent your data properly. And overfitting is that it fit too much, like this one. So what you really want when you build that deep neural networks or machine learning algorithms, you want to have some kind of balance. You don't want to have a underfit, or you don't want your model underfit compared to your data, and you don't want it to overfit, and then you want to have something just right. How you can do that? Yeah, the reason is that we want to have a underfit, overfit is that a lot of time if you have like for example, like under high barrier, there's a high biases means underfit, and then overfit means high variances. And then if you have a like high variances, then it also provide a lot of errors. If you have a high biases, it also provide a lot of errors. So you don't have something just in the middle. So that is kind of right machine learning's algorithms. And then when you have an overfitting, one of the way that you could actually minimize overfitting is kind of regularizations. There's a two type of regularization, is L1 and L2, and its main goal is discourage some of the more complex or flexible model so that you could avoid the risk of overfitting. So pretty much it will minimize the learning rate. So what was the general procedures or way to remove high variance underfitting or high bias underfitting or high variance is overfitting? High bias means that your model underperforming, which means accuracy is not up to the threshold. The way that we could actually improve your model is that you either have more features, which are more input variables, or maybe you could train longer, like rather than doing one-time training, maybe you could do about 10-time trainings, and also you can use more advanced model. If you have a high variances, which means that your model is okay with the training data, but in the test data, your model doesn't perform well, which means that your model fit too much on the training data. In that cases, you have to use more data or apply regularizations and maybe try less features. So machine learning training is kind of art and science, using the science such as machine learning, but at the same time you have to find the right fit with the art. So let's talk about the convolutional neural networks. There are actually two advancements. I would say two really big advancements in machine learning is that one is image recognitions. Second is natural language processing. That really help or actually make all the thing is really, really advanced. There isn't a whole lot of difference between machine learning and statistics up to when we talk about image recognitions and natural language processing. For the image recognition, convolutional neural network is the best way for image recognitions problems. So CNN is, we call that image-specific artificial neural networks, such as image search recognitions, face recognitions, or face verifications, self-driving car, and more. And the concept is coming from brain visual context where many neurons have a small region of a visual field. We talk about feature and later on in our presentations, so you will see more detail. The name of a CNN actually comes from convolutions, one of the most important operation and calculation in CNN. We also gonna show in our training later slide. The first CNN network is LessNet5, which can classify digits from handwritten numbers. We're gonna see more about the transfer learning. Is that probably one of the most effective way to apply CNN. Its advantage of CNN compared to DNN is that CNN could read the data as 2 or 3-dimensional, compared to DNN is just only 1 dimension. So for the image recognitions, it become much more powerful because we see the image as a 2-dimension or 3 dimensions. And then it will provide less parameter, which means much less computing power to train image data. So let's talk about image data. Let's say when the computer sees this image, actually it sees the picture value. This PNG data, if you actually import the data into computing numbers, then it goes something like this. As you see that, you could kind of see same shape, and 0 is probably blank. And then high numbers such as 255 is dark. And then low numbers such as 6 or like something now 7 is become very small numbers. So now this picture is represented by 28 by 28 pixels. So this is not really good quality picture. However, if you have a good quality picture, then this pixel become lot bigger. It go up to like couple thousands. But the key here is that your image data, any kind of pictures, could change into the numbers. And you see that if you click this pictures and go to property in your screen, you could kind of see that 1300 by 1300, which means that it has a 1300 X and 1300 Y pixels. It's a huge data point. When you process image data on deep neural networks, what happens is that, or any other model in machine learning, you actually change this 2 dimension to the 1 dimension. Such as 20 by 20 pixel data go into 1 dimension, which means 784 input data point. And then imagine how much weight you have to carry in. So if you do image data training with a DNN or other machine algorithms besides CNN, it requires a lot of computational power. When you actually stay as a 2-dimension, it becomes a lot more easier to train. That is a reason that CNN become very popular. For example, this picture has about like 2356 and 2304, and then this 3 means that when you see the image data, you could see that either 2-dimension or 3-dimension. 2-dimension is actually black and white, and 3-dimension is RGB, which is color. So usually you got 3 dimensions. So if you actually convert this data into 1 dimensions, and then it becomes 30 million feature going to DNN, this takes almost forever to train the image data. So what CNN does is that it actually looking at data either 2-dimension or 3 dimensions. If you look at about the architecture of CNN, we go by one as a more detailed informations, and it has input layers, usually about 4 dimensions, with a 28 by 20 times 1 or 3. Either one is color, one is black and white, and 3 is actually on colors. And then we actually the first one is going to be the number of the picture is going to go into trainings. So input layers, convolution layers, and pooling layers, and another convolution and poolings, and then flattened layers, and then fully connected layers such as deep neural networks, and then which is output layers, which is output. Compared to DNN, which is input layers and hidden layers and output layers, CNN has more complicated architectures. So input layers, usually about that, so 3 dimensions. If there's a 1 to the end, and the first and second is going to be the pixel size, and then 1 is going to be, if it's a 1 is a last dimension, which means black. If it's 3, which means a color. And if you actually process about 60,000 images, and it's going to be 4 dimensions. So CNN, the input data set feature is going to be always 4 dimensions. DNN is going to be always 1 dimension, 2 dimensions. So convolution is pretty much a mathematical combination of 2 functions to produce the third functions. CNN has filters. We're going to talk more detail about these features as we actually multiply this feature into this 3 by 3 matrix, and we got the value. So 1 times 3, 1 times 1, 2 times 1, and 0 times 0, 0 times 5, 0 times 7, minus 1 times 1, minus 1 times 8, minus 1 times 2, then you got a minus 5 value. And we go on. So this is image data, and this is a feature of a CNN, 3 by 3 features. So we got all those numbers. As you see that minus 5 is coming from theirs. And then you got the oldest number, and then you notice that 8 is the largest one, which means that this area represents these things well. So filter could be many different formats, but also filter is representing image feature identifier. This, if you actually change this into the image, it's gonna be straight line. This gonna be is a horizontal straight line, the vertical straight lines, then it's gonna be kind of shape. So when you got the high number in certain feature, such as these cases, which mean image on this area more likely into straight line. So convolution kind of working this way. The filter go into each area and then find about what it will represent. So it find about slope in this kind of slope in these features, and this kind of slope in these features, and this kind of slope in these features. So convolution is kind of filter, finding best filter in image perspectives. And then pooling is just to making sure that it could reduce some spatial size so that you could actually compute faster. So there is a max pooling, then also average pooling. Max pooling is more popular than average pooling. What it does is that if you are pooling with a filter 2 by 2, means that it go by 2 by 2 and then find the most highest number. In this case, minus 2 from this 2 by 2. In this case, 8 from this 2 by 2, and it's going to be 0 for this 2 by 2, and it's going to be minus 3 and 2 by 2. Flattened layer is that it is actually converting all those kind of 4 or 5, or actually 4-dimensional pooling layers into 1 dimension, so that you could actually process things much faster. And then fully connected layer is kind of deep neural networks. Basically, it has a flattened layers, and then couple of the hidden kind of layers, such as fully connected layers, and it connect to the output. So the fully connected layer is working like a nuance. In fully connected layer, detect a certain feature of images, like a nose and mouth and eyes. So in this case, this nuance represent might be nose. This nuance represent by certain types nose 1 and nose 2, nose 3, and it could be represent I1, I2, I3. So in this output, you probably get the more value for nose type 2, and in these cases, it could be more value from I type 2 and things like that. So output layer is pretty much output representations. So if you get a 10 output, which means there's about 10 output, whether it's going to be 0 to, probably 0 to 9, it could be the one that has a 10 output. And then the interesting about this output layer is that the resulting vector for digit classification programs such as, let's say it's going to be 0 up to there, then as you see that it represents 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then that means that the 10% probability that is going to be 1, and 10% probability is going to be 2, and then 75% probability that image is going to be 5, 0, 1, 2, 3, 4, 5. So that you actually are looking about the 5 is the most popular answer. The machine learning is most time is about the probability. If there's about 10 output classifications, and then you pick the one which has the most probability, and the softmax function provide that information. So as you see that for CNN model, input dimension is going to be 4 dimensions, such as 20,000 images, and each image is represented by 1400 times and 1400 pictures and the colors. And then output is a 2, which means about 20,000 dimensions to 20,000, and then 10 output. So this 20,000 is going to be number of the records, which is output, and then second dimension is the number of the classification, such as 0 to 9. It could be car and truck and van and bicycle and things like that. Actually, every year there is a competitions about image recognitions, and then one of the most popular one is the LANET, and developed about 1990 before 2000s, and then the one that really making most popular was the AlexNet. It just developed about 2012, because it using the CNN, and then it actually beat other competitions more than half. It's about 85% accuracy for the image recognitions. And then thing is this get better when we apply more CNN algorithms. The ResNet, which is competition winner in 2015, is less than 4% error rate, which is amazing. We're gonna talk more detail about this one later on in transfer learning, because we will using some of the pre-trained model to any other machine learning implementations. CNN implementation is one of the most popular deep neural networks, and it is pretty much go-to model for all those image-related problems, such as image classifications, X-ray diagnosis, face recognitions, and face verifications, and object detentions, and autonomous vehicles. I'm actually very excited about our next topic, recurrent neural network and natural language processing. Actually, this is the one that I'm working at this moment in my current positions. Recurrent neural network is the model that use sequential informations. The reason that recurrent neural network become popular is that it is very useful when our input are dependent. When you actually talk about other machine learning algorithms, all those input data, input features are pretty much independent to each other. However, in the same or in the situation that the data become very much dependent, such as sequential data and RNN, recurrent neural network, has most effective machine learning algorithms for those kind of data. Because this RNN has a memory feature that captures previous informations about what has been calculated so far. Let us look at the example. The basic RNN structures and algorithms is shown below. As you see that there's an input such as x1 go into the model, and it get processed, and it provide the output model. And when x2 was input into the model, what happened is that this RNN neurons also have information from previous input such as x1. And x3 has the same situation. It also received the information from x1, x2. So now, when you talk about this y3 as an output, it has information from x1, x2, and x3, and so on. The basic structures about RNN model has two units: gated recurrent unit, LSTM, or long short-term memory unit. The gated recurrent unit is a gating mechanism in recurrent neural network, and it has been shown to exhibit the better performance on smaller data set. And then GRU actually has a fewer parameter than LSTM, so that it could actually train faster. However, LSTM, which is long short-term memory unit, actually become more effective when you talk about RNN and also natural language processing implementations. It has a 4 gate, such as input, forget, gate, and output. LSTM, remember the values over arbitrary times intervals, and 3 gate regulate the flow of information into and also out of LSTM unit. The basic kind of popular implementation is that, such as text notation or filling in the missing output. So it actually same number of the input and also same number of the output. When you see the situation when there is a missing word or vocabulary in a sentence, then this one is able to fill in those missing informations. Another implementation is a sentimental analysis, such as pharmacovigilance signal. When you read some of the text, and then you could actually analyze whether this text means or represent some information, whether this text is about adverse event or other informations. Or when you read this text, you could kind of see that, oh, this sounds happy, or this sounds positive or negative. And then another implementation is kind of picture descriptions. When the picture is read, and then output is going to be the information about the pictures. And also machine learning translations. Input going to be the English, and output is going to be French or Spanish, or checkbox development or any other things. RNN actually very useful implementation for natural language processing. The natural language processing is pretty much in the area of artificial intelligence, of the human language interactions and implementations. So basically, the computer read some of the language, and also it provides descriptions and analysis about those language text information. So our input data will be some text, language, and output data is could be descriptions or other text in the language. Let's look at some of the sentiment analysis. So input data is, we actually implement the embedding the process, which means represent each word to the vectors or numbers. What I mean by that, we actually read the data, input data as a language, some of the vocabulary, and we convert that vocabulary into the numbers. For example, if go into words such as, I am happy, like here's a completely, and it convert into the embedding process, and then it become E1852, which is about 50 vectors of that informations. And the output data could be representation of the softmax output, such as 0.07, 0.13, 0.1, and 0.70, which represent very unhappy, unhappy, very, and very unhappy. So using that, this output, NLP could predict the output of this text is going to be very happy because it has highest probability of 70%. As you see this one. So if you go into more detail about this information, for example, this input data is I am smiling. So now in NLP process, this I, the vocabulary is going to be converted into some of the numbers, and it go into LSTM process. And then M also going to change into number using the embedding process. It go into the next LSTM. And then smiling also go into the embedding process and convert into the vectors, numbers, and then it go into LSTM. So this part has a memory from I, am, also combination of a smiling, and using this process for in the natural language processing, it also provide the output. In this case, very happy. Recurrent neural network is applied a lot in the many industry, and then it is one of the most popular implementation for machine learning, and it will be more implementation you could see in the futures, such as speech recognitions, music generations, sentiment classifications, machine translations, video activity recognitions, and name entity recognitions, DNA sequence analysis, and also checkbot. I'm also very excited about our next topic, about the transfer learning. It is the one that I currently working on, but at the same time, it is actually make machine learning implementations and training become much easier than before. Let me tell a story. Let's say we try to training SAS programming, some people. You have two options. One is experienced programmers. The other option is novice programmer which never programmed before. So in general, we can ask the questions, who will learn faster? And who will be much more effective or cheaper to train? Yes, usually the experienced programmer, such as who knows about Java or Python, are learn SAS program much faster than the people who never programmed before. Exactly the same way. Transfer learning is that we already train our model with some informations, and then we actually convert or using that already pre-trained model with other implementations. So in a way, the machine learning method, it is a machine learning method where a pre-trained model is reused as a starting point of the model development for another or similar task. So you might wonder, how it could be applied. Before we go in that direction, let's kind of talk a little bit about some of the characteristic of the machine learning model. For, let's say, image recognition model, we actually train the model. In early layers, kind of detect about edge detections. And when you go into middle layers, it starts shaping. Each nuance represents some shape of the images. And then when you go to kind of layer, later layers, and then each nuance represent more high-level feature detections. So as model progress, the layer or nuance from the layer model, later layers actually represent more high-level features. So let's kind of looking about current pre-trained models such as VGG. VGG is one of the most popular one. That it is also free, available in the public, and it has a two architecture. It's either 16 layers or 19 layers, and then it is a CNN model for image data, and then it already trained with a 14,000 images with a 10,000 class objects. And then it has the parameters such as weight and biases. There are about 100, almost 140 million parameters. And then if you're gonna train again, it will take about a week. And then it costs a lot of money because you need a GPU to process and train this model. However, all those parameters in this pre-trained model VGG are available in public. So let's see how we could actually implement transfer learning in our new problems. First, we select the pre-trained model. Let's say you select the VGG. And then we import pre-trained model into our programs. So this VGG is already trained with the 14 million record images, about the thousands classifications. So we import this already pre-trained model into our programs, and then we could actually determine which layer we're gonna train again, or which layer we're not gonna train. You could right now let's say you have about the 6 layers here, but you could decide to train maybe last 2, or we don't train that again. And then we decide more layers of the imported pre-trained model. Right now there is only 1 layers in our side in F6. We replace that with our new layers here, and then we define output differently. Let's say you're gonna have a 2 in output, and then we actually prepare new data. Right now there is about all the images we train it, but right now we're gonna focus about certain images such as X-rays, and then we determine that we actually decide what is output is gonna be of these layers, and we compile this and then train again. In terms of VGG, we need about 14 million images, but in a pre-trained model, setting about the proper output layers, we might need about a couple thousands. So it is actually saving a lot of money and saving times. So you wonder why transfer learnings. We actually talk about it. We could train model much faster, so it become cost effective. In many cases, sometimes you don't have choices, because finding right data is sometimes very very hard and very difficult. So lack of data decide that we're gonna go into training pre-trained model in a lot of cases. As you mentioned, that there's a lot of pre-trained model. For image data, there is a exception, insertion model, ImageNet, ResNet, VGG model, and also ResNet model, things like that. For language data, there's a Google, Word2Vectors, and Grove as an embedding process, and then UML Fit or BERT and Elmo is one of the most popular language model out there. So when you do some of the high-end implementation, in many cases, we start with a pre-trained model, and then we prepare data accordingly, and we actually set up some of the model so that we could actually apply it to our problems. So let's talk about how machine learning, AI impacting our lives. First is probably the prevalent in our implementation, voice recognitions. I have a young children, and then time to time I notice is that they actually talking to Siri. So, such as Alexa, Siri is one of the most popular NLP implementation. So it is the voice recognitions. And then Amazon or Netflix or Spotify using machine learning for their recommendation systems. The chatbot is probably one of the most popular one in terms of customer services. So when you open that, some of the website, they actually pop up small window saying that, how can I help you? Most of the time, those kind of pop up window actually the chatbot, and you are initially talking to the machine, not to the humans. Good thing is that this chatbot, once you set up this chatbot, it will provide a quick and easy communication between customer, and that it will work 24/7. I think about last year that Google introduced AI Assistant. It's a system that accomplishing real world tasks over the phone. It's amazing what it could do in the futures. And also Amazon introduced the Amazon Go, cashierless grocery store. And what happened is that you actually scan your phone when you walk in, and then you actually pick up your items into your bag. And what happened is they monitor you using the CNN image recognitions, and then when they grab it, they notice. When you return it, they also notice too. So they charge based on what you actually selected. The funny thing is there's no line in cashier, but there's a line outside waiting to get in. Yeah, I mean, it happened about a couple years ago, and the IBM built AlphaGo to beat the best Go player in the world. We think that Go is so complex, so machine probably never gonna beat human, but AlphaGo actually beat that best Go players with a short time of trainings. Whenever I talk about machine learning, and then when I say about this, terminators, then people always got it. I mean, there is a debate about how much machine learning should be applied or implemented in certain areas, such as military. There's a lot of people actually go against it about this part, and something that we should regulate, and some of the machine implementation in certain area. But when you talk about AI machine learning, then if you kind of hint about the terminators, then people usually get it about the machine learning implementations. So how the machine learning implementation industry? And let's talk about some tool. There is some machine learning programs such as SAS and R and Pythons, and then SAS also has a great interface tool such as SAS Visual Data Mining and machine learning interface, and you could actually do a lot of visual and easy to use machine learning implementations. And also, if you look at about the SAS Via, there also has some of that machine learning procedure that you can use it. And R and Python is probably the popular machine learning implementations, and it's also available into the website. And also, there are a lot of good machine learning packages too. And then there are also very interactive, easy to use tools such as SAS Visual Data Mining and Machine Learning Package, or IBM Watson's, and Microsoft Azure, and Google Cloud and H2O. So let's talk about why that AI machine learning is so popular. And it is actually very innovative. It actually helps us to solve the problem that we weren't able to solve before. And it actually provide about new business revenue and also developments. And it is actually cost effective. it could automate a lot of the tasks and work, and that it might have a chance to replace or enhance some human resources. Andrew Ng is one of the most popular AI implementation. He's a co-founder of Coursera, and then he was leading that Google Brain and also Alibaba for last couple of years. Right now, he actually doing that some AI machine learning based on the mutual, I think that the investment funds. But he kind of say that the pretty much anything that human person could do or think in less than a second, we could now automate with AI. So there will be a lot of implementation in terms of innovations and cost effective purpose. So there will be more and a lot of AI implementation in the futures. And some cases, not all, but it could be more accurate than general humans in some of the applications, such as X-ray diagnosis, things like that. A lot of people actually ask me about how they could start about machine learning. Whether we like it or not, machine learning gonna be change a lot of different things. So first step is we have to admit that machine learning is there, and it will change many things. And then I would recommend that reading or learning of machine learning, either take courses. There's a lot of online courses, free videos and schools. And then as a programmer, then I I love to do hands-on programming. So best way to learn is hands-on programming. So do exercise. You could participate Kaggle competitions with others, and then start follow other people. There are a lot of good machine learning materials and also machine learning teachers. Even there's a lot of them is free. So try to follow them and try to keep up with them. And then start implementing in your organization, even if it's very small and simple. That way that you could actually start learning about it, but at the same time you can actually evangelize the machine learning for your department and your organizations. The hardest part is any innovations in any new technology or new idea is actually starting. And I applaud you that start about machine learning and also taking these courses. So let's kind of keep it up. And then if you have any questions and if you have any comments, and please let me know. You could find me. You could send an email to my personal email address, and also you could actually send any information or request about the LinkedIn. I'm very active LinkedIn and social media, so you could actually contact me through the area. And please let me know how you're doing, and also let me know if you have any questions. Once again, thank you all for attending Machine Learning Pre-Seminar Conference at SAS Global 2020, and I look forward to seeing you all for next SAS Global Conference. Thank you. Please let me know if you have any questions. Thanks. Bye.